Hello everybody, today we're going to talk about SSV computation for a fixed given frequency. When I say fixed given frequency, usually we have n of s here, right? Here we have n of s, and for a given frequency, j omega, right? For a given frequency, let's say omega equals 1 radian per second, right? Okay, and in that case we will compute j dot 1, right? This matrix related SSV, single structured volume, structured single volume. Okay, and why do we need that? If you look at the playlist that this video is located, you will understand why we would like to do such a calculation. Okay, and the calculation is this. We are just trying to compute this actually. Okay. Infimum d in a given d, okay, d times n times d inverse, okay, and this value is an upper bound of the I written m, but it's n, and there can be some confusion in the coming moments. If I write n instead of m or something, you kind of get what I'm saying, right? We are only talking about a given matrix, just one matrix. There's no other matrix. Okay, we are interested in right now. Okay, and all right. So first of all, structure single value of n. Okay, here n is a n by n complex matrix. Okay, we have n of s, and delta, like capital delta, like the structured single value, structured uncertainty. Okay, and we have some information about this uncertainty structure, right? Let's say we know that it's in this form, diagonal, right? And the diagonal entries are like complex numbers, delta 1 in complex, right? And so is the delta 2. Okay, so let me get rid of this. We have some information about the uncertainty here. This is the uncertainty. Okay, and we would like to compute structured single value, right? And structured single value, as in the sigma plot, we are all familiar with the sigma plot, right? Okay, and it can be something like this. Here, this capital delta, right, and also bold double delta indicates our specific set. Okay, what do you mean? What do we mean by specific set? For example, let's say we have some information about our uncertainty, and uncertainty is something like this, for example, where again delta 1 and delta 2 is in complex numbers, right? Okay, or maybe delta 1 times identity, right? 2 by 2 identity, and delta 3. Let's say we have that type of uncertainty, Okay, that can be the case, right? Okay, and capital delta, the uncertainty set, can also be, for example, these are, or this is square and this is square, and the whole uncertainty, the delta, is square. However, it sub blocks, right? Sub blocks can be rectangular, right? So we will think about that type of situations as well, right? And okay, however, step by step, if we can move, right, we will understand the general idea. All right. So one, we have some uncertainty. We have n of s. Okay. Again, what we see, or like what we do in sigma plot, right? Sigma plot. For example, we have n of s, and for each given frequency we have, let's say, j omega 1. Okay, we have n by n, right? n by n complex matrix. Okay, so we can compute its single values, all right? And all single values are like positive real numbers, right? Okay, and get the maximum of it. Let's say it can be something like this. Let's say n is like 3 by 3, and we have, in each frequency, of course, we have 3 single values, and get the maximum. Okay, and depending on the problem, we would like this maximum value across all frequencies to be less than gamma, depending on the problem. Or maybe you have some scared or normalized case where you like it to be less than 1, right? So something like that. I mean, considering the previous videos, previous kind of small lectures, right? We have talked about this. So far, we are familiar with the control problem, right? Like reference signal, like control signal, output signal, etc., right? And we have some planned and we have some uncertainty, right? And considering the uncertainty from that general control problem, we have, let me get some, yeah, from that we have something like this. Okay, this is U, no, this is W. W is like the exogenous signals, and this is Z, regulated output, right? And this is Y, measured outputs, and this is Y delta, and this is U delta, and this is U, right? So from given typical control problem, let's say, do we have some space? Okay, let me get some space. Okay, usually what we have is like something like this, right? The typical control problem, right? And we haven't said anything about the dimensions, etc., right? Okay, so I'm looking at the problem, and here this p is like nominal, right? And we can also consider the uncertainties, right? Let's say p, and this is like p, yeah, this is p matrix or p system actually. Okay, and then p nominal identity plus w some system, and then delta of s. Okay, so we know this and we know this. I mean, considering the problem that we have, right? These are the kind of things that we have knowledge about. Either they are directly given, or we have some information about the uncertainty, right? And then by using our information, we can just compute nominal planned, right? Representation, transfer function, and the weight corresponding to that uncertainty, right? Okay. And let's say, I'm speaking of course, the general cases, right? Okay. So let's say we have something like this, okay? And from the nominal or usual control problem, we have like this type of problem where we also we are considering the uncertainty phenomena, right? Okay. And then, for example, in the first videos of this playlist, right? If you check them out, you'll see typical H infinity representation often, right? Okay. Here P augmented, right? And again, W is exogenous input, and Z regulated output, Y measured output, U control signal. Okay. And this is H infinity framework, where we are only considering exogenous, right? The disturbance signals, and also we are trying to mitigate the effects of exogenous signals on Z, mean our objectives, right? Okay. And let's say error tracking abilities or something, right? This type of signal, this type of issues we are dealing with in H infinity control design. Okay. However, we are not directly focusing on the uncertainty that plant will have, right? Okay. And when we say H infinity is robust, we mean robust against the disturbance signals, external signals, right? And however, it is not robust considering the uncertainty that plant may have. Okay. So if we have some information about plant uncertainty, right? And I'm not specifically talking about the parameter uncertainty, which is a type of uncertainty. However, like the uncertainty that can be distributed across the frequency domain, right? Okay. So this is H infinity framework, right? And after that, let's delete all this. Now we leveled up in a way, and we are considering this case now, right? Again, disturbance, regulated output, Y, the measured output, okay, and control signal. This is like Y delta, right? And U delta. So now the problem is similar to H infinity. However, we are also incorporating the uncertainty information into the problem. And the problem is this: design such K such that, considering M and also considering the structure, it is not like full. I mean, it can be full delta, right? When we say full, we mean like unstructured. In that case, our progress, if we have like quote unquote full or unstructured uncertainty, the problem would get much easier. Okay. However, if we have some information, if we have some structure, right, and we have some information about that, and we parameterize our delta, our uncertainty structure or block, right? Our uncertainty here, this is the uncertainty block, right? And we can design a better cache, better controller. When we say better, it will have better performance, and also, yeah, I mean, it will have better performance. What do we mean by that? The effects of, right, disturbance signals on Z objective signals, right, will be mitigated best when we say optimal, right? Okay, so to be able to design such a cache, first you need to eat your vegetables. I mean, to be able to design such a cache, right, first we get familiar ourselves with the stated problem. Okay, what is the stated problem? For a given, now let's focus on this, right? Okay, let me get rid of this and also this, right? For a given n of s, for a given, oh, there's something wrong with that. Okay. For a given n of s, and also given uncertainty structure block, right? And like the sigma plot, right? The sigma plot, where we have something like this. Plot SSV, or yeah, something like this, for example. And by the way, SSV would be, I mean, I'm kind of exaggerating, or maybe let's plot here, right? Let's plot here. Wait a sec. I'm looking at this. Where is that? Okay. Here, let's say n is 2 by 2, and we have like 2 lines here, right? Okay. And we will have one line, right? And mu n of s. Okay. Actually, it would be better for us to just indicate something like this, right? Okay, let me get close to that location. Mu delta, right, of n j omega. Okay, so we will have something like this. And okay, let's call it SSV plot, right? So for a given n of s, for a given transfer function matrix, right, for a given LTI system, right, and I kind of don't want to say LTI. I mean, let's just restrict ourselves and say for a given transfer function matrix. Okay, for a given transfer function matrix, the thing that we are really familiar with, right, and acquire, right, obtain SSV plot. This is our main goal, right, the first objective. Let's focus on that. However, before focusing on that, just obtain this object. Okay, I'm going to state that object mu, right, mu, again delta, right, and for a given, let's call it w1, and let's call it w1 equals 1 radian per second, right? Okay, so this is a, and let's call it just n is a, again, n by n complex matrix, right? Just compute this, and we know the structure of the uncertainty delta, right? Okay, this is our main problem, right? This is our main problem, and after that we are going to focus on now we learn about the main problem, and now we are going to focus on how would we compute structured single value for a given complex matrix. Okay, this is now the video is starting in a way. Okay, that was the intro. Okay, so let's continue. Okay, we are looking at this, and after that here, for example, this is n of s, right? And we just substituted s with j omega. Okay, and omega x, like omega x is like 1 or 2, some constant frequency, and let's compute it for frequency. It's 1 rather than per seconds. Okay, and our complex matrix, and this is a complex matrix, right? Each entry is like a complex number, and compute its SSV, and this MATLAB code is only here. This we are just initiating our defining our n of s, right? And after that, eval frequency. This command just gives us the, for example, this is 1, right? Here this is 1, and eval frequency command. Here we have transfer function, just give us some omega x, and it will give us the complex matrix corresponding to that frequency. Okay, and here it is the output, and again this is a complex matrix. Okay, and now we will look at 5 cases. Let me get this 5 cases. Okay, case 1, full delta. Let me write it, full delta, n by n. Okay, and case 2, looking at this, delta, like small delta times identity, right? Where small delta is a complex number. Okay, and case 3 is a diagonal form, and I'm going to specifically write something like this, like something like that. Okay, diagonal. However, for example, this is diagonal as well, but this is repeating diagonal form, and this is more like general diagonal form. Okay, and we have case 4 is the mixed delta, where we have the mixture of these 3 cases. Okay, what do we mean by that? For example, where delta might have the form delta 1 times, for example, repeating diagonal, right? And delta 2 and delta 3, for example, right? This is just diagonal form, and this is, let's say, 3 by 3 unstructured uncertainty, right? And we would have 2, 3, 4, 5, 6, 7. Okay, let's say we have 7 by 7 n of s, or n complex n matrix. Okay, let's not worry about n of s right now. N of s here, and our delta is like, again, okay, 7 by 7. Okay, and its structure its structure here is given by this. Okay, so compute SSV for that uncertainty case. Okay, all right. And if you look at this, each subblock is square, right? This is square 3 by 3, and this is 2 by 2. This is square, and this is identity times some delta, and this is square mixed. And I'm going to call that square because each subblock is a square, right? Is a square complex matrix. All right, and now I'm going to write case 5 again, mixed delta and rectangular. And in that case we can have something like this. For example, let's delete that. Okay, this is square, for example, and let's call it delta 2, right? And delta 2 is 2 by 1. Okay, and here delta 3, this is 3 by 4, right? Okay, coincidentally the given matrix is like 1 2 and again 7 by 7. However, not each subblock is square, right? This is rectangular and also this is rectangular. Okay, so it is not like a convention, right? Conventional thing to say like case 1, case 2 or something, but I just written them down. And throughout the video we are going to, or in the videos I guess, in the playlist, we are going to look at these 5 cases. Okay, and also lecture might feel like very messed up in a way. It's messy, right? And that's correct. I try to, tidy up the notes a little bit, however, like, or organize the lecture, right? Some topics, however, it doesn't go as planned always, right? Okay, so we have 5 cases, and and again let's write the problem again, right? This is N is like a complex matrix. Okay, and we know the structure of delta. Okay, and this creature is a very hard thing to compute. Let me just say that. Okay, and however we have some information about that. It is hard to compute that. However, it is not that hard to compute this creature. Okay, so we have data set, right? And we have like 5 cases for that. And for a given data set, we will construct our D set, right? And D set is made out of D elements, right? Such that delta times D equals D times delta for delta in capital delta, the uncertainty set. Okay, so they commute, right? The matrices are such that they commute, or each entry of that set commutes with all of the entries of the uncertainty set, delta set. Okay, so it may sound complicated, however we have only 5 cases, right? And let's focus on the first 3 cases, first of all, and then we are going to, you know, check 4 and 5. And I am looking at this. For example, first case is full data, right? Unstructured. Okay. And maybe I should copy that, right? Copy and paste. Okay. So for that case, our data is D times identity where, or such that D is in positive real numbers. It's positive. Okay, it's not like a Hermitian or something. It's positive real numbers. Okay. And for the second uncertainty case, I am looking at this. D is made out of D terms such that D equals its Hermitian, right? Hermitian, or rather H, or rather, I guess physics people indicated with a dagger, right? Is like Hermitian. Okay. And also positive, and it's in complex, right? N by n. All right. So I'm looking at this, looking at my notes, and here we have case 3. For case 3, let me check MATLAB actually. I don't want to make a mistake at this stage. Okay. Case 1, case 2, case 3. Yeah. Okay. Just diagonal. For that case, we have diagonal di. Each di is in positive real numbers. Okay. And we will basically construct our D matrices or D set, right? The parameterization that we need to construct. We will just do that considering our uncertainty and then using just given 3 quote-unquote rules. Okay. And so it depends. However, it is straightforward to construct the D set or the structure of the D, all right, the parameterization. Okay, we're going to talk about this in more detail. So, and for this case, this is going to be the last case. But what was the problem? The problem is this, right? And for this problem, we minimize or infimum, right? We will have something called dl as in left and dr as in right. Okay, again sigma max, right? dl and dr inverse. Okay, for uncertainties, this is complex math. This is uncertainty. For uncertainties where subblocks might be rectangular, we will have this type of case, right? And this is like more general, right? Also, dr and dr, they are not separate matrices, they have some connections. So like some entries of the matrices, they're like same. Okay, and we are going to look at some examples with that problem. All right, so let's move on. let's move on. This is case 1. This is case 1. And okay, this is case 1. Here is called full delta, mean unstructured uncertainty, right? Okay, and we are going to, what was our n matrix? Let's record that for that. 1 2 3 5. Okay, let's record that. 1 2 3 5, right? I already messed the expressions. Okay, so we have this n, and we compute for j omega, or just I, right? Okay, we have some, let's call it n of s, but we have some n 2 by 2 matrix. Okay, and now again let's recall what was that matrix, right? And this is that matrix, right? We just computed it for the given frequency, right? Here these are the right computations, and this is our n matrix. Now we are going to compute its SSV, structured singular value, for unstructured uncertainty case. Okay, and here this is delta, right? Actually it should be something like this, and this is our D set, right, where commutation, right, the entries of the D commutes with the entries of all elements of delta. Okay, and this delta sets. Okay, and for that given case, since we know it's like full, right, we have some parameterization that we can apply, and this is that parameterization, just D times identity. Okay, so in a way we are just tuning one parameter, that is D. Okay, and again this the problem where that set indicates this set for this problem. Okay, it indicates the structure of the uncertainty. Okay, and this is correct, this is correct, and this is the upper bound representation. So it is hard to compute structured singular value. However, it's easier to compute this expression, right? And because you can use, I mean, LMI techniques, right? And okay, all right, now to compute, by the way, it's a simple problem, and we are going to talk about this in detail, right? And just to represent or the idea, I'm going to talk about first FMINCON. FMINCON. FMINCON is a built-in MATLAB function, and if you have some structure where you have some t and you input some parameters, let's say that's cost computer, right? Cost function. If you have some like d1, d2, etc., or just a parameter, and it gives you the cost, right? Cost function, and it gives you the cost. You can use FMINCON. Okay, and again fmin and con is for constraints, right? And because we will have some constraints on D, let's say, I mean not, I mean exactly, for example, these for that specific problem they must be positive real numbers. Okay, and we can also constrain it, right? Let's say D cannot be greater than 1 million or something. Okay, just to make things easier. And you can use FMINCON for that type of optimization problems. All right, especially if you have like analytical problem, right, where you can express the costs in closed form in a way. Okay. All right. Let's read the comments as it is, right? Full data set, and for that given data, our D is like this, single D and D times identity, and D is a positive real number. Okay, first three case it's written here, full data, D times identity, and for delta times identity, repeating diagonal uncertainty is it's set full delta, but we mean like D like positive Hermitian, and I mean, since I said Hermitian, you directly assume complex matrix, but better to express that explicitly. Okay, so for diagonal uncertainty case, we have diagonal, right? We have again diagonal D matrices. Actually, not D matrix, but just D1, D2, D3, where all of them positive real numbers. Okay. And okay, so let's look at this. Yeah, this is the cost function. This is cost function, and here this is our given matrix. We are going to supply that function with one complex matrix, that's, and also D, we are going to also supply D, right, here, and it will give us the cost. When we say cost, we mean this, right? Okay, just give me some D and I am going to give you the result of it, right? And what was the problem? Cost. What was the problem? The problem is infimum D in delta, right? And minimize this term. So just this is like a cost, right? Cost, give me some D in that set, and I will give you, or the function will give you some cost, and FMINCON will try to minimize that using D parameters. Okay, so that's the case, right? And basically this is D times N times D inverse, right? And since we have some structure, since we have our D parameterization is this, right? We just directly written something like that. And for that case, okay, if we write something like this and D is like 2 here, it will give us the cost. Okay, and here we are looking at minimize the cost with respect to D, right? And this is FMINCON, right? Basically this is how you just use FMINCON, right? And first you need to supply input the function, where your function is like that. You need to input the parameters, and it can be vector, right? You need to input the parameters and it will output the cost. Okay, so this is like anonymous function representation, you know about that. And XOR is the point where you start your tuning parameters, right? And since we have only one parameter, just one D, right, one dimensional, I just written 1, and again this is 1, right? And this is like, since I want it to be positive, I written like the minimum value is like a really small positive number, and upper bound is like 10. I could have easily written 100 or 1000, right? Okay. And we could also written nonlinear constraints on our D, right? Where we could impose some nonlinear constraints and also some options or something. However, I have not used that. And also 1, 2, 3, 4. These 4 parameters I haven't used them. And okay, after FMINCON will basically compute the D parameter, and I call it dvec. And since the structure is something like this, our delta, right, for a given delta, we will then compute D matrix, and dvec is the parameterization, and D matrix is the really the matrix, D matrix. Okay, so for a given D, let's call it dvec. Right, there is some parameterization, and it will give us D matrix, just D, and we will use it to compute. We will use it to compute upper bound for SSV. Okay, okay, and compute the cost for the minimizer D. Yeah, minimizer D. That's the answer. Okay. Here, just check this expression. Again, notice this is like, let's call it dx and dx inverse. Dx is the thing that we just found, right? Okay. And this is upper bound for SSV. Okay. And in addition to that, we also computed just like the spectral radius of n and also sigma max, right? Okay. Why? Because SSV is something sandwich between this and this. It's like a identity, right? And okay, and here I also, to compare or to check in a way, use mu SSV, MATLAB's mu SSV function, right? You just need to input the complex matrix, and also here you need to input the structure of the uncertainty, and uncertainty is like 2 by 2 complex, right? And that's why you need to input 2 by 2, right? And we will see how to use mu SSV, right? And after that, it will give us bounds, upper and lower bounds, right? And also some information, and we will talk about this. And after that, we are just interested in upper bounds. Bounds will have 2 numbers, and the first number is like lower bound, and second number is upper bound. And okay, after that, the code output is this. Here, this is the SSV that we computed with FMINCON function, and this is the structured single value that we computed with mu SSV. And for full or unstructured data, this equals this. This is an identity. Okay, so that was case 1. Okay, so let's check case 2. And wait a sec. And our second case is repeating scale of delta uncertainty. Here, just something like this, n, and just delta, 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 or delta times identity. Okay, just compute that, right? Okay. Just forget the block diagram that I written, okay? Just that's not 100% correct, because we are only interested in this n and for a given structure uncertainty. Okay, and the structure is this, just repeating scale of delta. Okay, and for every delta we have a corresponding d set, right? And such that this given condition holds, right? And for that case, our d, the structure of our d set is this. It's made out of Hermitian positive complex matrices. Okay. All right. And since we are interested in 2 by 2, right? Let's recall our problem. What was our problem? Let's recall that. 1, 2, 3, 5. Okay. This is our problem, right? And 2 by 2. So in a way, we need to find, or we need to find a parameterization where d is 2 by 2 and Hermitian and positive. Okay. And okay, let's recall what Hermitian means. First of all, if we only have this type of constraints, right, and 2 by 2, we would write something like this: d1 j d2, right, d3 j d4, and d5 j d6, d7 j d8. We would write something like this. However, we also have this constraint, Hermitian. What does Hermitian? Hermitian is like transpose, and also you conjugate each entry. Okay, so if you consider this constraint as well, right, and also the positiveness, basically this is the parameterization. This is the parameterization that you will kind of acquire, right? Okay, and this is the d, right? 2 by 2 Hermitian positive complex matrices. So we parameterize our d set by using these 4 numbers, d1 dot 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 d4. Okay, and they are positive real numbers. Okay, so our problem just, it became, we kind of reduce our problem to that, this line, right? Okay, so just let's solve it, right? When we are just given d1 dot 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 d4, and this is the cost. Okay, again, like in the previous case, by using FMINCON, right, we have some cost function, and we will give d1 d2 d3 d4 real parameters, right, and it will give us some cost, and this is the cost. This is like the sigma max, right, for a given d1 dot 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 d4, for a given di, right, di, where I is like 1 dot 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 4, for a given di, compute this term, sigma max of dn, right, dm, I written m, dm d inverse. Okay, this is the cost. Okay, so again the same comments, right? This is like full d, quote unquote full d, and this is the parameterization for that constraint, Hermitian positive definite, right? just these two representations are like equivalent, right? Here D1, D1, D3, J, D4, D3, J4, right? D3 minus J, D4, and D2, here D2, okay. Okay. Let's continue, right? And this is the, okay, this, wait a sec, this is the cost function, and maybe I should have written another anonymous function. That term looks really long, right? Here D and D inverse and SVD and max, right? Okay, we are just interested in computing sigma max of that D and D inverse for a given D. Okay, by using D, right, by which we parameterize our D matrices. Okay, so let's continue. We kind of get the idea, right, now. And I just, since we have D1 dot 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 D4, right, and D is like a vector, D1, D2, D3, D4, right? So, and also they are positive real numbers, and that's why I squared it. I just here check the objective function works, if works, right? And I just supply some D, and for our n complex matrix, it give me some cost, okay? And all right, let's continue. So although that may look complicated, just look at this line again, FMINCON, right? This is like the same line. What change? The first starting points change. This is like, just give me some positive random number. This kind of indicates that, okay, again, this for parameters, right? Arguments, I just entered empty matrices, right? And because I don't have that type of constraint on D values, di, basically D1 dot 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 D4, right? Okay, and now I'm looking at this. This is the lowest value, this is the upper value of our D, right, that we impose on. And since we have 4 D's, right, again, this is 4 and this is like 4, and that change basically compared to the previous problem, right? And after that, it will give us D vec, right, like D star, and then we will compute our D matrix, right? This line computes, this line does that basically, and after that just compute that. What is that? This is D star, and when I say star, I'm not just minimizer D matrix, right? I'm not talking about the Hermitian or something. Okay, inverse sigma max. Okay, just compute that. Okay, this line does that, and again the spectral radius and sigma max, right? And also the mu SSV, MATLAB mu SSV function is 2, 0 means that type of uncertainty, right? That type of uncertainty. It's 2 by 2 repeating, and the next 0 is like that. It indicates that the fact that it's repeating diagonal uncertainty. Okay, again we written down the MATLAB mu SSV value and FMINCON, the SSV that we computed with using FMINCON function. Okay, let's continue again, and this is the third case, and this is our diagonal structured uncertainty. Okay, again our D set, right, commutes, and also the corresponding D set is this. We have some given D set, and for a given D set for a given delta set, we have some D set. Okay, this is like the just by definition, right, in a way. And this is the structure of our D set. Okay, again, these are like the things that we are familiar with. And here, this is the parameterization of D set. In the previous problem, we have like D1 dot 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 D4, 4 terms to tune, right? And for that problem, we have like only 2 D terms, D1, D2, right? And here, case 3, structure delta set diagonal, right? And corresponding D is like this, real, positive real, right? And this is the D matrix representation. And this is the cost function, right? For a given n, and also given D parameters, compute the cost function. All right. And since we have only 2 D's, this is like the dimension of the problem. And again, the starting point is just start from a random, and I'm squaring it to obtain element-wise square operation, just to have positive numbers, right? Because round end can give negative numbers. Yeah, I just okay. I wanted to make sure of that. And okay. By the way, now I'm looking at this, I feel like, I mean, the structure or the dimension is like D1, D2, right? So this term is dimension of it 2 rows and 1 column, right? Or something like this. So I'm not sure about if I feel like that would give us 2 by 2 matrix. I mean, I checked that the code works, but I kinda got hesitant. Okay. All right. Again, this is to like the minimum value, maximum value, right? The same cost function, right? And after getting the D values, just obtain the D matrix corresponding to that, and and then the corresponding cost, basically, just calculate that, right? And spectral radius and sigma max, and also MATLAB's mu SSV. And this is the structure. Let me write that. This is the structure. This is 1 by 1, right? And this is 1 by 1. Just write them like that. And just using display command, right? And MATLAB's mu SSV and FMINCON, the SSV that we computed, right? They are like same. And okay, now we are going to look at the case 4. And since it has like mixed uncertainty, we needed to have a bigger dimension, right? And that's why I'm now considering this n matrix, right? Is 5 by 5, right? Okay, again, this is the transfer function, and we are only looking at a given frequency, right? So at the end, we have 5 by 5 complex matrix. And now we are going to consider a random, by the way, an uncertainty case where we have repeating diagonal uncertainty, right? We have repeating diagonal uncertainty, and just a scalar uncertainty, and 2 by 2 unstructured sub uncertainty, right? Okay. So we have 3 subblocks, and for that the corresponding D set will also have like 3 subblocks, right? And let's look at them one by one. For that type of repeating diagonal uncertainty, D1 is full, right? And D1 is Hermitian full matrix. Okay. Right? Maybe repeating diagonal delta, the corresponding D is Hermitian. Okay. And for diagonal delta is like diagonal real, right? Diagonal and real D's, okay. And full delta, our D is just is scalar and positive real. Okay, so this is like the 3 rules for delta set. This 3 rules that we need to keep in mind to construct our D sets, right? And if we can kind of construct our D sets, then we can parameterize it, and then we can just solve the optimization problem that we have, right? We can impose that or represent our optimization problem, right? Okay. And so considering these 3 cases, these 3 rules in a way, identities, let's look at the subblocks, right? What is that type of uncertainty? It's called repeating diagonal, all right? The first case. So what is the D corresponding to that? Hermitian, right? This is it. Hermitian, okay. D1, Hermitian D. For a given diagonal, this is 1 by 1 diagonal, by the way, right? For a given D, it's like D2 is real number, just real and positive number, right? Okay. And then for a given full delta, right, unstructured delta, D is scalar times identity, right, such that the dimensions agree, right? Okay. And now we have the structure of our D set, and then we will just go one step further and we will try to parameterize it, right? Again, like in the previous problem, this is like Hermitian, 2 by 2 Hermitian, that type of parameterization, right? And this is for that just a real number, right? Real and positive number, and this is it, and this is D6 times identity, right? Here, maybe you like to look at that. Okay, so we parameterize it. So at the end we have 6 terms to tune, right? Optimize over, and this is the problem that we are looking at. I'm going to delete all of them, all of the things that I've written. So okay, that can be my thumbnail, I guess, right? Okay, so now let's keep that parameterization in mind, right? And now we are going to solve the problem, and this matrix is that matrix. Yeah, basically we are defining that n matrix, right? Okay, I especially written that down in that form. So for example, this is omega 1, right? We are computing omega, or we are computing SSV for that, right? And let's say we have omega 2. We are just going to compute that, and right, something like this. So we can just compute for our frequencies, right? After you are done with that, the only thing that you need to do is to write a for loop, right? Just divide all the frequencies, right? Discretize it, and then compute, just the compute SSV values, right? For each corresponding complex matrix, and then you will have, for a given structured uncertainty, you will have SSV plot. This is omega, right? SSV plot. Okay. Okay. Here, this is, we know what that is, and I mean, this matrix, right? This matrix and this, they're just, this line, I mean, right? They're just same, right? Let's look at that. D1, right? D1 and D3 plus J, D4. Okay. Oh, that's wrong. This, like, it must be minus. Okay, hopefully okay, it's the code version is correct. Okay, and this is D2. Okay, D5 here, and D6. The code is correct, by the way. I checked it. The only thing that you need to change is to make plus minus. Okay, and okay, so since we have 6 terms, D1 dot 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 D6, right? Okay, just generate a random, yeah, this is correct, runs, and just normal 6 comma 1, it will give us 6 comma or 6 cross 1 vector each, just selected from a normal distribution. Okay, because I think if you write or 6, it's going to give you a matrix, but I wonder why MATLAB hasn't give me any error for that. Anyway, in for the previous case. Okay, let's continue that. Since we have 6 D's, right? Just now we have some, just D1 dot 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 D6. Just give me the parameters or values for that parameters, and I will give you the cost. This is the cost function, and I will give you the cost. Okay, just using these parameters, minimize that cost. Okay, and this is exactly what FMINCON can do, right? And there is analyticity in the problem inherent, right? And that's why FMINCON is like the first choice. If the problem is like were to be extremely complicated, again an optimization problem, but really complicated, and you have like a couple of parameters to tune and really incredible constraints, you would use genetic algorithm type of optimization, heuristic optimizations, right? Okay. And again FMINCON, right? And this is the cost function handle, and this is the starting point, and these 4 arguments I don't supply, and this is the minimum value, and this is the maximum value, and we parameterize our d such that d1 dot 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 d6 each one is positive and real also, right? Real numbers. Okay, so that was convenient. We arranged the terms, we parameterize our d matrices such that it was in a form that is suitable to use with FMINCON function. Okay, again just obtain FMINCON will give us the d star, and then by using this line we will get d matrix star, and then we will get this right? And again spectral radius and sigma max, and also MATLAB's mu SSV. And here let's try to understand the notation. First 2 by 2, or rather first term is 2 by 2 repeating diagonal, right? Whenever we say repeating diagonal, is like just give me the dimension, right? And then to indicate 0 as the second term. Okay, so what's that? And then only scalar delta, and then full 2 by 2 delta, right? This is like the scalar. When we say scalar, we mean 1 by 1, right? And then full 2 by 2. Okay, let's say 3-dimensional 3 by 3, but repeating diagonal uncertainty. We would then use, usually we would write 3 by 3 if we had like full delta, right? Okay, unstructured delta. But for repeating diagonal we would write just 3 0. Okay, just we would make it 0. Okay, to indicate we have repeating diagonal uncertainty, and we have the result, right? This is the structural singular value that we computed, and this is the MATLAB's output, right? And this is the again spectral radius and also sigma max, and the term is closer to that, right? Okay, sigma max, and this will be the final one, I guess. No, I feel like this will be the final one. It says, yeah, that should, right? Case 5. Okay, now SSV computation for a fixed frequency, right? And this is 7 by 7 transfer function, and for a given specific function I just written like this, right? Okay, so we have it's like case 5. We have 7 by 7 uncertainty, right? And we have 7 by 7 complex N matrix. Okay, this is the structure of our uncertainty, right? And maybe I should make this screen as the thumbnail. Okay, that looks cool, right? Don't you agree? All right, so this is the really hardest case, right? Rectangular case. And this is square. This is square. However, these two are rectangular. And whenever you have some uncertainty where one of the subblocks is like rectangular rather than square, you would have just rather than D and D inverse, you would have the problem of sigma max D left and D R inverse. Okay, you would have that. This is like more general form, right? DR, DR, and it is not complicated. Just follow the rules, right? And we have additional one rule here. So for the square ones, we would do what we would do, right, in the previous case. For example, repeating scalar, right, and Hermitian D, D1. D1 is Hermitian because delta is repeating scalar form, has that kind of form, and D1 is Hermitian. Okay. And this is scalar delta, and D is real, just a real number. Okay. And here we have 2 by 3. Yeah, this is important. 2 by 3, and this is dimension. And what would you do if we have like delta 3 in 3 by 3? What would you do? How would you parameterize the D object? You would parameterize it such that D times identity, right? You would do something like that. Okay. And also dimension would be 3 by 3, right? Identity is dimension. Okay. And we just written the same thing, and just for the dimensions to agree, right? The identity matrix's dimension is in that form, right? Again, one more time I'm going to show you. Second dimension goes to left, and first dimension term goes to right. Okay. When I say right, I mean this, right? Okay. So again, we do the exact same thing, right? We do the exact same thing, and this is wrong. This is just, it should be 2 times 1. Okay. All right. We have another error, and again this dimension goes to that location, and this dimension goes to that location too, right? Okay. So here D1 is Hermitian, D2, D3, and D4, these are real numbers, right? And we again just parameterize D1 matrix, right? As in the case, this is like Hermitian parameterization. We are familiar with that now. And just to parameterize, and now we use D1, D2, D3, D4, right? And the next would be D5, the next variable that we would use, right? D5 for D2, and D6 and D7, and just following the same, I guess, operations, we have DL and DR parameterizations, right? And it is nothing complicated actually. Just follow the rules, right? You don't need to even think about this. And again, this is like 7 by 7 transfer function, and this is for omega equals 1, right? Omega equals 1. And okay, and I written 2 enormous functions, and here let me just check if I can show them. Okay, yeah, they're in the same picture. Okay, that's great. So let's delete them, right? Let's delete them. So we know the DL parameterization and DR parameterization. We have like 7 D1 starting from 1, right? D1 dot 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 D7. And if you give me D1 dot 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 D7, I will give you DF and DR. Okay, the corresponding matrices, two matrices, right? Okay, and these two functions basically does that. Okay, and if you look at the structure here, this is and this are the same, right? Okay, and this is like the only D5 here, only D5, and this is only D6, right? And this is only D7, right? Again, same for the right DR. Okay, so let me delete all this to have some space. Okay, again, as in the case, we have objective function, and this is like df, right, and dr. Just give me one d, right, because I parameterize our df matrix and dr matrices, right, and just give me d1 dot 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 d7, and I will give you dr and dr matrices, and then you can just compute the cost, right? Here, this is just one more time, df and dr inverse. Okay, just give me d and then dr matrices, and then compute the cost. Okay, and now we have the objective function, like the cost function, and since we have 7 D's, right, to tune, this is the cost, and this is start from a random positive number, positive point in R7, right? Okay, and this is just make this is the smallest value, and this is like a really small real positive number, and that's how I constrain the fact that di's are positive real numbers, and this just I could have written like 100 or 1000 or something, right? Okay, and after d vec get dr, dl and dr matrices, and then compute fmin SSV. This is the SSV that we computed with by using FMINCON function, and then spectral radius, and then sigma max, right? And this is the final mu SSV and MATLAB's built-in function, and 2011. Okay, wait, let me show you. Wait a sec. We have the structure of uncertainty, and this is repeating diagonal of uncertainty, and the dimension is 2 by 2, right? And that's why we would write 2 comma 0. Okay, and this is only 1 comma 1, right? 1 comma 1, and this is 2, right? This is 1, by the way. Let me just show you. Let me correct that. This is 1. That was a mistake. Okay, I'm sorry. And this is delta 3, right? And this is just 2 comma 3. Okay, and this is 1 comma 3, right? So 20, 11, 23, 13. Okay, 20, 11, 23, 2 comma 1. I'm sorry, 2 comma 1. Okay, that was a mistake. That should be 1. That's 1. Okay. Actually, it's better to revise your own mistakes, right? And that way some viewer also can see, hey, I think there's some mistake or something, right? That will be more interaction, I feel like. Okay. And then finally just print the results, right? And this is the SSV computed by using FMINCON function MATLABs, right? And this is the SSV, mu SSV output, mu SSV output, right? And these are the spectral radius and sigma max, right? And this is like 2.1974 and 2.1974, right? They coincide. And so finally, just a couple of words. And mu or mu SSV, I feel like this is old. I mean, it can work, but mu SS or wait a sec. Yeah, no, mu is totally a function in MATLAB, and it will give you bounds and rho d. Rho d is d parameterizations, right? And in a way, this is not the parameterization that we use. This is MATLAB's own parameterization. And let's say for that type of uncertainty, right, we have that type of structure. So repeating diagonal, again the second term must be 0, right? 2 by 2, but second term 0, right? And this is 1 by 1, right? This is 1 by 1 because it's 1 by 1 complex matrix, right? Complex, yeah. And here just write 2 by 3, right? This is 2 by 3 for fourth term. Let's look at that. 3 by 3, okay, 3 by 3. And this again repeating diagonal, right? You would usually write 3 by 3, but the second term is 0, okay. And then 2 by 1, again full matrix, right? And just you would use that type of syntax, and then MATLAB would supply you, after you computed your SSV, MATLAB would give you df, d left, and I'm sorry, d right, okay. Here we can see that, right? Okay. And let me check if there's anything. Yeah, just one more thing, I guess. And yeah, this is more general case, right? This is the case where each subblock is square, right? Okay. So again, let's check the problem. This is from this example and small note from excerpt from Keminzu, John C. Dyer, Essentials of Robust Control. And it says example 10.2, right? Okay. And for a given uncertainty here, this is, what is that? This is the repeating diagonal uncertainty, 2 by 2, but second term is 0, right? And this is 1 by 1, right? Okay. And this is 2 by 3, and this is 2 by 3, and this is 2 by 1, okay. So MATLAB program gives these bounds. This is lower bound and this is upper bound, and here the R and the R. Okay, so I'm looking at this. Yeah, okay, that's it. So that's it. In the next video, I'm going to explain how to do the same computations by using YOLMIP, right? And SDP T3 is the SDP solver that I use, right? Okay, that's it. And